things about self-avoiding walk or how to count self-avoiding paths. So now we are going to focus on percolation. So let me recall you what that is. So we have a parameter P, which is between 0 and 1, which is fixed. Okay, I'm considering the interval closed. Of course, the process is a bit boring if P is equal to 0 or 1. But we have a graph, okay, which is a set of vertices and a set of edges. And for most purposes, we are going to consider the case of ZD. And we are going to consider PP, a probability on the state space, which is 0, 1 to the E. So to each edge, we are going to associate a value 0 or 1. And these values, they are IID Bernoulli random variables. So they are independent Bernoulli random variable with parameter P. So by this, I just mean that the probability that E may get E is equal to P, it's equal to 1. Okay, and well, independence allows you to compute the probability of a product of such events, okay, for different edges. Okay, so now let me introduce a few basic definitions. So we say that two vertices are connected. Okay, and by this I mean that they are connected for the environment omega. Okay, so I draw this value 0 or 1 for each edge, and this is going to be fixed. If I can find a path of open edges that is linking the two vertices. So if there exists a path Zi, I equal 0, yes? Yes. Of course. Thank you, Ricardo. Yes. Now this makes sense. Okay, so if there exists a path of finite length, starting from x, ending at y, such that for all I in 1k, omega zi minus 1 is equal to 1. Okay, and okay, by saying that this is a path, I'm implicitly saying that this thing is an edge. Okay, and this property for the remainder of the lecture, I will say that the path is open if every edge is on the path is open. Okay. Second, we say that vertex x is connected to infinity for omega, if there exists an infinite path that I equals 0 to infinity, that 0 is equal to x, and the same thing is omega zi minus 1 is equal to 1 for I larger than 1. Okay, so here there is something that is kind of implicit when I say a path. When I say a path, I mean something which is self-avoiding. So I'm not allowed to visit twice the same points. So it's not really important for the first definition, because if you have a path linking x to y, or open edges, you can just erase the loops and you will get a self-avoiding path. For the second definition, well, okay, of course, if you have a loop going from x to x, you could have, if you don't have this self-avoiding in the definition, this makes this not a good definition. Okay, so here when I'm saying path, I'm always assuming a self-avoiding path. Okay, so now I will just spend a few minutes on some technical details, but I think they might be important, and they are generally overlooked. So it's equivalent to say the following two things. So the first thing is x is connected to infinity. And second is the number of y in ZD such that x is connected to y is equal to infinity. So it's the same thing to say that x is connected to infinity and to say that x is connected to infinitely many vertices. Okay, and maybe I should have added this here. Okay, and when it's important, I will add omega here in the notation, but most of the time I won't. Okay, so I guess this lemma looks reasonable for most of you, but maybe even obvious, but okay. Does anybody has an idea for how to prove this? Okay, so 1 implies 2 is actually not difficult, but 2 implies 1 is, well, you need to do something. So. Okay, so that probably means that this requires a proof. Okay, so let's start with the easy way, the easy implication. So, okay, so. Okay, so first thing we can say is that, well, this thing gives us an infinite open path. And if we take all the vertices on that open path, by definition, they are connected to X. Okay? So in particular, the cardinality of this set is infinite. Okay. Now, 2 implies 1. So what we are going to do is the following. So maybe I will construct explicitly the infinite open path, and to construct it, I will use the fact that I have infinitely many finite open paths. Okay, so I will call gamma 0 set of finite open paths starting at X. Okay, and what I have by assumption is that the cardinality of gamma 0 is equal to infinity. Okay, because for each y in this set, I have a path. For 2 different y's, the paths are distinct. Okay, they are not disjoint, but that's not the matter. They are distinct, so this set is infinite. Okay, so now I start from X, and well, X has 2D neighbors. So among these neighbors, there will be, I can find one for which there are infinitely many paths in gamma 0, which use the edge zero, Z1. Okay, X has 2D neighbors. So there are 2D choices for the first edge of the path in gamma 0. Okay, so among these 2D choice, one should correspond to infinitely many paths. Okay, so we choose Z1 such that X Z1 is the first edge of infinitely many paths. Okay, and we set gamma 1 to be set of the set of gamma in gamma such that X Z1. Well, let's start with X Z1. Okay, it's a finite sequence. I'm just fixing the first 2 members. Okay, and then once you've done that, you can iterate. Okay, so Z1, it has, well, if you take a path that starts from X and Z1, then for the second step, you have 2D minus 1 possibilities. Okay, because the cardinality of gamma 1 is infinite, there is one possibility that must be chosen for infinitely many paths. So you can fix a Z2 that corresponds to infinitely many paths. And then you iterate this. So, okay. Iterating, we find Zk k larger than 0, such that gamma k is the set of gamma in gamma such that starting with x z1 zk then the cardinality of gamma k is equal to infinity. Okay, and then it's over, of course, because this sequence gives you an infinite open path. Okay, the fact that there exists, I mean, the fact that this is non-empty tells you that in particular the edge zk minus 1 zk is open. Okay, and this is the case for every k. This zk gives you an infinite path. Is this last part clear? So to conclude, we must check that the path z, okay, let me write it zi I larger than 1 is open. Okay, so for this, we just have to check that and we said z0 equal x by definition. I have not defined what z0 was. Okay, and the fact that this is equal to 1 is just a consequence of the fact that gamma I is non-empty. Okay. So if gamma I is non-empty, it means that there exists an open. Okay, so remember that. Okay, here is gamma 0. Remember that gamma 0 is a set of finite open paths starting at x. Okay, so this means that if you have a path in gamma 0, all the edges in this path are open. Okay, so particular for a path in gamma I, okay, it uses zi minus 1 zi as an edge, so this edge has to be open. So the full path has to be open. Okay. So is the proof clear? So now the next thing we are going to do is so we want to understand basically long-range connectivity properties of percolation. So one first quantity one may want to study is just the probability that one vertex is connected to infinity. Okay, so here I'm writing theta p, and there is no dependence in x, but this is just because this thing is the same for every x. So the reason for this is just that our lattice is periodic, so and the distribution of omega is invariant by the symmetries of the lattice. So, okay, so for the percolation environment seen from every point, it looks the same. Okay, so this is not something I want to give a detailed proof about. There is something which is more worrying in what I wrote there. if you've done measure theory, you know that you're not allowed to take the measure of any event. Okay, so the question is, does it make sense to look for the probability of this? Okay, so if you haven't done a course in measure theory, just don't worry too much about this issue. But the idea is that basically the only kind of events for which probability makes sense, they are, well, first things that only involve finitely many edges. And then you're also allowed to take, well, if something is, okay, when the probability of something makes sense, we say it's measurable. And well, if an event is measurable, you can say that the complement is measurable. And if you have a countable union or countable intersection of measurable events, you still have something measurable. Okay, so basically, well, the set of events for which you can take the probability, it's stable under some operation, but it's not, okay, it's not all, it does not contain basically the full set of parts of 0, 1 to the e. So basically, what we want to do is to check that this thing belongs to the product sigma algebra, okay, because what we are considering, the sigma algebra we are considering on this set is the product sigma algebra. Okay, so let me. Okay, so let me just check measurability. I will just do this once. For the rest of the course, you will have to convince yourself that basically, as soon as you're writing something that you can talk about and you're not using axiom of choice, you won't have problem with measurability. But I think it's good to check it at least once. So, okay. So let me first check that the event x is connected to y is measurable. So we let gamma xy, the set of paths. Okay, I'm not saying here. I'm not saying the set of open paths. The set of the whole set of paths from x to y. Well, to say that x is connected to y, it's the same thing as saying that, well, there exists an open path linking x to y. So it's the same as the union over gamma in gamma xy of the event gamma is an open path. Okay. So now, this is measurable because this is an event that involves only finitely many edges. Okay, if you fix gamma, this is measurable. And now this set is countable. So we have a countable union here. So therefore, this is a measurable event. Okay. Now, if you look at the event x is linked to infinity, well, this is the same thing as saying that for every n larger than 1, there exists y such that x is connected to y, and y minus x is equal to n. Okay, so here, this is just the L1 distance between x and y, and this corresponds to the graph distance in ZD. Okay? Here I'm just using the lemma. Okay, I'm saying if x is connected to infinity, then it's connected to infinitely many points, and if it's connected to infinitely many points, it has to be connected to a point at each fixed distance. Okay, so now this is just the intersection over n larger than 1 times the union of y in ZD such that y minus x is equal to n. And now what do I have? I have x connected to y. Okay, so we have seen that this is measurable. This is a finite union, and this is a countable intersection. So everything is fine. Okay, so any questions so far? Okay, so now we are going to go into more interesting things and study the properties of this function theta p. So if you remember what I said last time, what we want to prove, our ultimate goal is to prove that there is a critical value of p such that, below this value, basically, the set of open edges cannot conduct water on large distances, and above the set PC, it can. Above the critical value, it can. So, the first thing we are going to do is identify a critical value which is defined in terms of theta p. And this is the main result of today. So there exists PC in 0, 1, which is such that theta p is equal to 0 if p is smaller than PC, and theta p is positive if p is larger than PC. Okay, and a natural question is what happens at PC, and okay, I will talk about that later, but mostly it's a very challenging open question, and people don't know. Okay, so to prove this, we'll use 3 steps. So the first thing is that we are going to prove that the function theta p is non-decreasing. So it's kind of obvious in a sense. If you make p larger, you have more open edges, so more open paths, so you're more likely to be connected to infinity. However, you need to do some things to translate this intuitive idea that larger p means more open edges. Okay, so. And basically, this gives you the result but with PC in Well, this doesn't exclude the fact that PC could be equal to 0 or equal to 1. Okay, so the two other steps are to prove that theta p is equal to 0 for p small, and step 3, theta p is positive for p large. Okay, by large I mean close to 1. Okay, so for step 1, what we are going to do is to fix p prime larger than p and prove that theta p prime is larger than theta p. Well, the idea, okay, we want to prove that somehow, well, if p is larger, you have more open edges. So what we are going to do is to construct, well, percolation environment with parameter p and parameter p prime on the same probability space in such a way that one is strictly larger than the other. Okay, that I'm going to construct omega p, so omega p e in E, and omega p prime e in E, such that omega p prime of E is larger than omega p of E for every E, and such that this thing is distributed like pp, and this thing is distributed like pp prime. Okay, so what's the way to do this? Well, what we are going to do is on each edge, instead of putting a Bernoulli variable, we are going to put more information, and an information which allows to construct a Bernoulli variable for every values of p. So the right thing to do is to put on each edge a uniform variable on 0, 1. So start with UE, a collection of independent uniform random variables indexed by E. So by uniform, I just mean that UE is distributed like a uniform variable on the interval 0, 1. Okay? And by independent, okay, I just mean that if you take any finite collection of edges, you have the probability that omega E1 belongs to A1, omega EK belongs to AK. Well, this is just the probability of omega E1 belongs to A1. The probability that omega EK belongs to AK. Okay. So, and I'm just calling P the associated probability. And now I define omega P of E to P is just, well, the indicator of UE smaller than P. Okay, so with this definition, you can check that well, the probability that omega EP is equal to 1 is indeed equal to P. Okay, also that these variables are independent. Okay, independent is directly inherited for the okay, I should have written U here. Sorry. So the independence for omega P is just inherited from the independence for U. And also by definition, we have that omega E P is smaller than omega E P prime. Okay, so now this is all over. What we have is that, well, if a path is open for omega P, well, then because of this, it's also open for omega P prime. Okay, so this just gives me that theta P is smaller than theta P prime. Okay, so well, this argument it's quite simple, but the principle is very useful. So this is what is called coupling. Basically, if you want to say something about two processes with different probability laws, you're trying to construct them on the same space with a joint law which has nice properties. Okay, and okay, in this case, it's not too difficult to find the right way to make this construction, but sometimes it can be much more tricky. Okay, so before we go through the second step, are there any questions? Okay, so now let us prove that theta p is equal to 0 for small p. Okay, so the observation here is that for 0 to be linked to infinity, basically I need a path, an open path of length n going outside of 0. Okay, if I fix n, I have an infinite open path. Sorry, necessarily I have an open path of length n. So. Okay, so now when you have an existential quantificator in an event, this means that you have a union, in fact. So this thing, you can say that, well, it's the union over all open paths, over all paths of length n starting from 0, that this path is open. Okay, so now you know that the probability is equal to the probability of the union over gamma in S n. Gamma is open. Okay, so I think this is the notation I had for set of self-avoidant by starting from 0. Okay, so now this is smaller than the sum over gamma in Sn of P. Gamma is open. Okay, and well, here I'm asking for n distinct edges to be open. So this is just P to the n. Well, it does not depend on gamma, so what I get is just this. Okay, and this is true for all n larger than 1. Okay, so in particular, what we have is that theta p is smaller than the lim sup when n goes to infinity of Sn Pn. And we know that this is equal to 0 if P is smaller than 1 over mu of Zd, where this is the connectivity constant of Zd. Okay, so well, this is just for the sake of having a good bound. Okay, you can just say that this is smaller than 2d to the n. Here say that this is. I should use a different color. Okay, so this gives us that PC has to be larger than 1 over mu of Zd. Okay, and so any questions so far for step 2? Okay, so let's go to step 3, and well, we want to show that theta p is positive for p large. And okay, well, what's easier to do is to prove upper bounds actually. So what we are going to do is to prove that 1 minus theta p is small when 1 minus p is small. And here, actually, we are going to restrict ourselves to the case d equal to. So why is this possible? Well, let's imagine that d is larger than 3. So then what you have is that the event that 0 is linked to infinity, well, it's larger than the event that there exists an infinite open path starting from 0 in Z2 times 0 to the g minus 2. Okay, asking that I have an infinite open path in ZD. Well, it's actually less restrictive to say that I have an infinite open path, but in the slice of ZD on which, well, all the coordinates larger than 3 are 0. Okay, so I'm not very good at drawing in 3 dimensions, but basically what I'm saying is that so let's imagine that this is Z3 and these are copies of Z2. I'm just I'm just trying to find this open path in this slice. Okay, and so now you have the probability of this, which is larger than the probability of that. Okay, let me write it like theta PD. And this is exactly theta P2. Okay, because well, this graph here is just Z2. Okay, so what you have is that basically theta P is increasing with the dimension. Okay, so it's sufficient to prove this in dimension 2. And now we are going to use a specific thing of dimension 2, which is duality. So, okay, I'm writing all the proofs in ZD, and most of the time they can be extended to other setups. So maybe it's kind of important at the end of each proof to know exactly what we've used. So for step 1, we've basically not used anything. Well, for the definition of theta P, okay, we have used the fact that the network, the lattice is periodic. For step 2, we have only used the fact that, well, each vertex has finitely many neighbors, okay, which is not really an assumption, because if a vertex has infinitely many neighbors, then percolation becomes quite boring. You have lots of connections everywhere, and you're always connected to infinity. Okay, and also, yeah, in the first lemma, when I say that being connected to infinity is equivalent to being connected to infinitely many vertices, this also uses the fact that well, our graph is locally finite. Okay, so now we are going to use something more subtle, which is called duality. So what's the idea? Well, we are going to start with Z2, and we are going to draw another graph. So what we are going to do is, for each edge E, we are going to consider an edge E star which, okay, is orthogonal to E and cross it in the middle. So this is just for graphical representation. So now if you look at Z2, okay, and this is something that really works only for planar graphs, so for graphs that you can draw in the plane. So the graph that is obtained with all these dual edges is called the dual graph. And basically, the vertices they correspond to the faces of my original graph. Okay, and I have these edges which are linking two faces, crossing edges. Okay, so if my lattice is L2, basically, the lattice L2 star, okay, it's just basically, well, it's Z2, but which has been shifted from 1/2, okay? Okay. The set of edges is what the set of edges should be. Okay, so Z2 has this particular property that it's self-dual in the sense that its dual graph is homeomorphic to itself. Okay, so the idea is that, well, it's easier to, okay, because we have this union bound in probability, that the probability of a union of events is smaller than the sum, it's easier to have bounds from above than bounds from below. Well, in order to have a good bound from above, basically we are going to work with a small parameter, which is 1 minus p. So we are going to consider a percolation process on the dual graph, which has now parameter 1 minus p. So we are going to define omega star E star, which is just 1 minus omega E. Okay, so basically we are going to define simultaneously a percolation process on the primal graph and on the dual graph. Okay, one is deduced from the other in a deterministic manner. Okay, there is no extra randomness here. And basically, the two possibilities you have is that either, well, the original edge is open and the other one is closed, or your edge E is closed and the other one, the dual edge, is open. Okay. So, okay, let me try to do some drawing. Okay, so this is 0. Okay. Okay, so let's stop here. Let's say that I'm just drawing a percolation configuration. I'm trying to draw a percolation configuration where 0 is not connected to infinity. And now let me draw the dual edges. So let's continue in orange. So the dual open edges, they are, well, they correspond to primal closed edges, so they are these ones. Okay, what's the important point I want to make here? It is that if you're not connected to infinity, this means that the set of vertices that are connected to 0 is finite. Okay, and now if you look around the set of vertices that are connected to 0, okay, and maybe a better choice here would be to look at something like this. maybe I want to put holes. I don't know. Okay. So if you look around the set of vertices that are connected to 0, basically you will see a contour, a circuit of dual edges that will go around them. Okay, so this is a geometric statement that I will not prove, but okay, basically if you wanted to prove something like that, basically you look at the set of vertices that are connected to 0. Among this set, you can define a boundary. So these will be the vertices which can be linked to infinity without visiting this set. Okay. You have 0. Okay, you have a set of vertices connected to it, but it can have holes in it. Okay. Then you want to say, okay, among these things, they are in this set. There is a boundary. Okay, so these are the vertices for which you can basically exit the set and never go back to it, go to infinity. And basically, if you follow the dual edges that are around these external vertices, this is how you construct the circuit. Okay, so okay. So now the idea is that this circuit, it's a self-avoiding path, and that we have obtained before an upper bound by basically using a union bound on having the probability of having a self-avoiding path. So we should be fine. So let's try to use this fact. Okay, so if 0 is not connected to infinity, then there exists an open circuit surrounding 0 in the dual graph. Okay. So we are looking at P of 0 not connected to infinity. We want to have an upper bound on this which is smaller than 1 to conclude. Okay, so it's equal to the probability of this. Now we need to say something else. So okay. So if you have an open circuit surrounding 0, then it must cross the positive real line here. Okay, I'm just identifying R2 with a complex plane. So in particular, okay, there is an edge in the form n plus 1 which is crossed by this circuit. Okay, so okay, so this is n larger than 0. Okay, so now what can I say? Okay, so now, well, if this happens, then I know that starting from this point, I will have an open path of length at least, so the minimum will be this length. Okay, so the length is at least, well, basically, I think it's 2n plus 4. Okay, in fact, that's 2n plus 3 because I'm just counting, I'm not counting this edge. Okay. So, okay, let me call this xn. So this is, okay, p times the probability that there exists a self dual open path of length 2n plus 3 starting from xn. Okay, let's forget about this p. Okay, and well, you know that this is smaller than 2d to the 2n plus 3 times p to the 2n plus 3. Sorry, 1 minus p to the 2n. Okay. This is okay. So in the dual process, the probability of having an open edge is 1 minus p because it's the probability of having the primal edge closed. Okay, and this is smaller than 1 if p close to 1. Okay, so here, in fact, this gives you an explicit bound on, so this is 1 minus theta p. Okay, and this gives you that theta p is larger than 0. So as an exercise, you can try to make this reasoning a bit more quantitative and show that PC is actually smaller than 1 minus 1 over mu of Z2. So how would you do this? Well, okay, so how does mu of Z2 appear? well, it's basically there. Okay, when you're counting the paths, instead of putting 4 here, because we are 2-dimension, you can just put S2n plus 3. But the thing is that here, you do not have this, okay? You have the full sum. So in order to get the right bound, you actually need to show that you can actually start this sum from a large n. Okay? It will not give you a bound on 1 minus theta p, but it will give you a bound on something that will prove you that theta p is positive. Okay, so it's not necessarily an easy exercise, but you can try to think about it. Okay, so this ends up the proof of the proposition. And this third step, it's where we have used really a property that is peculiar to ZD. Okay, well, at least a property which is peculiar to Z2. But let me emphasize that this is actually not so peculiar to Z2. So this proof actually works for any other periodic planar graph, periodic planar lattice. So let me try to tell you why. So the two lattices I've given to you last time, they were the hexagonal lattice. So you just have this hexagon pattern and you extend it to infinity, and the triangular lattice. And what happened is actually, if you take the dual of the hexagonal lattice, you get the triangular lattice, okay? So basically, for any planar graph, you can always construct a dual graph. And well, okay, I'm not going to make this work. Okay, so this you can make this reasoning with circuits also for the hexagonal lattice or the triangular lattice. Okay, this is ugly. But basically, yes, if you fix a point and you say that this thing is in a finite connected component, and you will have a closed circuit in the triangular lattice. Okay, so what can I say? Okay, now let me make a small digression about what is called side percolation. So you can change a bit the rule of the game, and instead of opening edges, you can decide to open sides. Okay, so let's say you start from the graph, and now you're given Vx, x in V, and you say that a path xi I equal 1 to k is open if Vxi is equal to 1 for all I in 1k. Okay, so you can play percolation on this. Ask yourself the same questions. What's the probability of being connected to infinity? Okay, it turns out that the proof that you have for percolation with the proof we have just presented just extend to that case as well. Okay, so you have to be a bit more, you have to replace this blocking circuit argument by another blocking circuit argument. But it's basically something very similar. So an exercise would be prove the same theorem for side percolation. Okay, so now the next question that comes is what can we say about the function theta p? What can we say about pc in particular? Okay, it turns out that for most graphs, PC is unknown. And there is not so much of a reason to think that PC will take a particular value. There is, however, some noticeable exceptions. There are some noticeable exceptions. And one of them is Z2. So So the idea is that because of the symmetry of the percolation and the dual percolation, the natural value you should conjecture for the critical point should be 1/2. It's when P and 1 minus P are equal. And okay, one way you can see it is that if you take a box n by n, basically you will have either one percolation path that crosses it vertically, or one, okay, it has to be orange, one dual path that crosses it horizontally. Okay? And basically when P equals to 1/2, okay, you know that these two things, they are disjoint events. Okay? If you have this, you can't have this. Okay, because this is blocking this. And if you don't have this, you have this. Okay, because the only way that you don't cross is basically if you find a barrier that prevents you to cross. Okay, now because of symmetries and because, okay, you have to be careful about what exactly is this square. I think it has to be a n by n plus 1 square, and I have to be careful about how things are designed on the edges. Okay, basically I want to make sure that the two lattices are the same. So I think this is basically how your boxes are. This This is what a 2x2 box should be. Okay, you want to make sure that the dual graph and the primal graph are the same. Okay, so when P is equal to 1/2, well, the probability of these two events are equal, okay, because the P is equal to 1 minus P, so they are equal, so they should be equal to 1/2. Because you have 1 is equal to P of this plus P of this, and it's equal to 2P of this. Okay, here I'm using the fact that the event are disjoint. And here I'm using P is equal to 1/2. Okay. So basically, what I said last time is that I'm expecting that above the threshold, basically, I'm crossing at large distances with probability 1, and below the threshold, I'm crossing with probability 0. So if I'm crossing with probability 1/2, it means that I'm exactly at the threshold. Okay, so this is kind of the, okay, so basically this is something that has been predicted in the 60s and that took 30 years to be proved. So what I would like to talk about now is an easier case when you can compute the value of PC. Okay. So I forgot to ask if there are any questions. Okay, so we are going to explore now a simpler case where not only we can compute PC, but we can even have an explicit expression for theta p. So it's a case of d plus 1 regular trees, and I'm going to take d larger than 2. So my graph is a tree. Okay, so it means it's a graph with no cycle, and it's d plus 1 regular, meaning that every vertex has d plus 1 neighbors. Okay, so this would be the case for d equal to. Okay, and okay, and basically all I've said so far, well, except the proof of step 3, it can adapt to regular tree. But this is not important because we are not going to prove here that PC is smaller than 1. We are going really to identify the value of PC. Okay, so theorem on TD, we have PC equal 1 over D. And this is also 1 over the connectivity constant of the tree. Okay, so this is the first exercise. Compute shows that Okay, and this exercise already shows you that on the tree everything is going to be simpler, because when you try to count when you try to count self-avoiding paths on the tree, it's not very complicated, because as soon as you're not allowed to meet other vertices, what it only means is that you're not allowed to backtrack, so that you will just go towards the leaves of the tree that you will never see. Okay, so this I will try to prove this now, and maybe next time I will give you the expression for theta p. So I will just quickly repeat step 2. So what we have is that the probability that, here, I will just take a vertex on my tree and say that it is equal to the origin or the root of the tree. So the probability that 0 is connected to infinity, well, it is smaller than the probability that 0 is connected to what I will call Tn, where Tn is the set of x at distance n from x, from 0. Okay, so when I say distance, I always mean graph distance, so just length of the shortest path that brings you to one vertex. And using union bound, this is just smaller than, the number of, the sum over Tn. That 0 is linked to x. And there is only one path, one self-avoiding path linking 0 to x. Okay, so this is equal to cardinality of Tn times p to the n. And this is just d plus 1 times d times p to the n. Okay, so if p is smaller than 1 over d, you can take this to infinity, and this will be fine. Okay. So now I want to show that we have not made some large overcounting when we did this. The idea is basically that, taking the sum here is not such a bad idea. So what can we do? So now we are going to prove that if p is larger than 1 over d, then this thing is positive. Okay, so it's going to be different. We are not going to do some lower bound stuff. What we have is that if you look at the event that the root is connected to infinity, well, this is just saying that for every n, the root is connected to Tn. Okay, I'm just saying I'm just using the notation here that x is connected to A. This is just the event union over y in A of x connected to y. Okay, so why is this true? Well, this inclusion is obviously true. And the other inclusion comes from the fact that, well, if this happens, then 0 is connected to infinitely many vertices. So it's connected to infinity. Okay. The good thing here is that this sequence of events is decreasing. So what we have is that theta p is equal to the limit when n goes to infinity of the probability that 0 is connected to Tn. So if we get a lower bound on this, we are fine. Okay, so now basically what we know is that if P is larger than 1 over D, then the expected number of vertices in Tn that are connected to the root goes to infinity, because this is what we have computed here. Okay, so the expected number. Okay, so I'm going to call this variable Zn. Okay? And what I want to show is that, well, the probability that this thing is positive does not decay to 0. Okay, so I want to show that this is larger than some c that does not depend on n. Okay, so I know that the expectation diverges. So maybe what I should do is compute the second moment and try to extract something from there. Okay, and this is something quite common, actually. When you do a reasoning which is concerning expectation, and you want to show that you have not made such a too big mistake, a mistake which is too big, basically you compute the second moment, so the expectation of the square, and if the expectation of the square is roughly equal to the square of the expectation, this means that probably you're not too far off in your reasoning. Okay, so let's try to compute the expectation of Zn square, and then try to see if we can conclude from there. Okay. So the expectation of Zn square, it's the expectation of the sum over x, y in Tn of indicator 0 is connected to x, indicator 0 is connected to y. Okay, I'm just writing Zn as a sum and expanding the sum. Okay, so it's just a sum of probabilities. X, y, in Tn. Zero is connected to x, and 0 is connected to y. Okay, so now I have to be a bit more careful because probably all these terms have not equal probability. So you have to see exactly. So I have 0 here, x here, y here. And okay, I'm going to assume that the distance here is n minus k, and the distance here are equal to k. Okay? If I have 2x in Tn, well, when they are going to the root, at some point they are going to meet a common parent. That might be the root itself. So this, every pair, okay, it will, my graph of open path, okay, it will look something like that. Okay, so how many edges do I have? Well, n plus k open edges. Okay, so the probability of this is just p to the n plus k. Okay, so now I have to find the number of x and y, of pairs x and y that corresponds to a given value of k. Okay, so basically, all the vertices in the tree, they have the same role. Okay, so I can choose x as I want. Okay, what's important is then the relative position of y for x. So I have d plus 1 times d to the n possibilities for k, for x. Okay, I have one possibility for y if k is equal to 0. Okay. This is x equal y. I have to count this separately. And if not, basically, I have to count the number of vertices that I have in this subtree, okay, which is of height, okay, in these subtrees. Because here I have d minus 1 branches going out. Okay, so d minus 1 times d to the k minus 1. If k is larger than 1. Okay, is 1 n. Okay, so this gives me sum from k equals 1 to n. D squared minus 1. Here I have minus 1, sorry. And d n plus k minus 2. Okay, and then plus d plus 1, d to the n minus 1, p to the n. Okay, so if I look at this, basically, it's not exactly this, but because of this term here. But it looks very much like a geometric sequence with a ratio which is larger than 1. Okay, so it pretty much behaves like the last term. So you won't have too much problem to show that this is smaller than a constant that depends on d and p times dp to the 2n. Okay, the last term here corresponds to k equal n, so it's n plus k equals 2n. Okay, so it's good because now I know that well, this is something like the square of the n. Okay, at first order, this is something like the n is really like dp to the n, and this is like dp to the 2n. Okay, so now I have to use something to conclude. So if x is a positive random variable, well, a non-negative random variable, what we have is that the probability that x is larger than 0, this is larger than, let's see, it's expectation of Zn, x square divided by expectation of x square. Okay, so this is actually a particular case of Pelley-Sigma inequality. Okay, so I'm going to prove this last. It's a one-line proof, so you can think about it if you want, and see how this can save us. So what we have is that theta p, okay, is larger than the limit when n goes to infinity of the probability that Zn is positive. Now we have that the probability that Zn is positive, it is larger than the expectation of Zn square over the expectation of Zn square. Okay, and well, this thing is just, so it's d plus 1 d to the n minus 1 p to the n square. Okay, now I'm going to use this bound here. C dp to the 2n and we just get that this is larger than, well, okay, d plus 1 square over d square times c. Okay, so this is larger than a constant that does not depend on n. Okay. So this thing is positive. Okay, well, actually, I mean, with this expression, you could even compute the limit. But let's not, if I do this now, I think I will make a mistake in the computations. Okay, and in any case, okay, we are going to compute theta p next time. The limit does not give you this thing is not sharp, so this does not give you a sharp bound on theta p. Okay, so does anyone has an idea on how to prove this simple inequality? Yes. Cauchy-Schwarz inequality. So it's exactly this. So what you have is that, well, if you look at the expectation of x, it's just the expectation of x times the indicator that x is positive. Okay? Then you can put squares. And this is smaller than, well, the expectation of x squared times the expectation of this indicator square, okay, which is just the probability that x is positive. Okay, so actually, well, you can look at it on Google. You can also, using this, you can also have a, you can even show that with positive probability, x is larger than a small constant times its expectation. So I think if you have this, then you have to put 1 minus theta squared here. Okay, but for us, being positive is what we want. So. And the proof is still one line, but okay, so well, the reason I wanted to present this proof, okay, so first it gives you a value of theta p in a practical case, but also this thing of computing, well, computing the first 2 moments of a quantity in order to deduce something about it. It's something which is quite common in the field. Well, it's sometimes tedious, but it's always useful. So just to give an example where it gives a kind of a striking result, because it gives not only a bound of theta p, but really the right value for the value of PC. Okay, so what we will, well, next time we will close this digression on concerning trees by having an explicit value for theta p. And you will see that actually this was not really needed. You can actually directly compute the value of theta p without first proving that it's positive. But I think this is, well, for an educational purpose, this is kind of useful. Okay, so are there any questions? Okay, so we will meet next Tuesday. And